All right. Well, happy Friday, everybody. Hope you guys are doing okay. Yeah, anybody have a midterm already? No? Okay, next week, maybe? That's when midterm season starts, and then it's midterm season until the end of the quarter, right? So, okay. I wanted to talk a little bit about avoiding using super assignment, okay? So I know I talked about super assignment and how it applies in scopes and environments and stuff like that, but then people are then tempted to start using the super assignment function. And I have to say, please don't use super assignment. I mean, it's generally, it's in the long run, I think it causes more problems than solves, okay? So let's say you wanted to update some kind of object foo. The bad way to do this, let's say all you wanted to do is just take the current object of foo, and then you're going to just tack on x squared to it, okay? So if the, whatever it is, if you take in the function takes in the argument foo, and then it's going to tack on x squared, and then update foo that way, okay? So for example, in your tic-tac-toe homework, you have to update the state of the game quite often, okay? And so here I'm not using state of the game, but I'm using just a stand-in called foo. All right, and so you might be tempted to use super assignment in this way. You'd say, so here we're calling this the add square bad function, and it takes in for its argument foo and x, and what it does is it updates foo by taking the current value of foo, combining it with x squared using the c function, and then it just returns that to foo using super assignment. Okay, and so if we were to run this, and I just uploaded this code into the week 3 module that just says avoid super assignment. That should be an R. Some R code there. And anyway, so if I load this up, and then we test this out, and we go, all right, let's say foo is 2, and then if I run this thing, add square bad function to foo and 5, we would expect it to return that it would update foo to be 2 and then the value 5 squared, so it should be 225, right? So if I run this, I would do that, okay? And the code ran, we can't really see what it did. And so we just say, okay, well, what does foo look like? And indeed, it looks like 225. And we're like, oh, great, this works. And we are tempted to move on with life. But this is where having this kind of super assignment is bad. Let's say you wanted to do the same thing. You wanted to modify this other thing where you're going to take some value, square it, and tack it onto the end, okay? So let's say we have a different object called bar, okay? And so here we would do add square bad, bar, comma 5, right? And what is this supposed to do? It's supposed to take 10, and then it's supposed to take 5, square it, and we should get 1025, right? Is that what's going to happen, though? Well, I'm asking you, like, it might feel like the answer should be yes, but I'm asking you this question so you're suspicious and you're going to say no. And let's just see what happened. What is the value of bar? Bar is still 10. So what happened when I ran this thing? Well, because of the super assignment, it took in the argument bar here, and it says, okay, I'm going to do bar and do x squared. So bar is 10, and then it's going to take 10, x squared is 25, and then where is it going to store it? It's going to store it in foo in the global environment. So when we ran this, bar remained 10, but then foo got updated to 1025. Right? You guys understand what happened in this code. Because of the super assignment in here, and it's pointing to foo and the global environment, even though I took in the argument for bar here, which was a value of 10, and I did 10 and I did attach 5 squared to it, it took that result of 1025 and it stuck it into the global object foo. Okay, so this is probably not what we wanted, and this is why I think super assignment is generally a bad idea, because super assignment is really like, if you're only going to have, first of all, I don't think it's a good thing, and it really only works if you only have one thing in the global environment called foo, and nothing else will kind of mess with that object, and there's no other time you would need to repeat the same kind of thing. Okay? So a much better thing is to write the exact same thing just without the super assignment. Okay? And so add square good, I'm going to make it a function of baz, so neither foo nor bar, but it's just an entirely different argument. It's a function of this, and what it does is it just takes whatever object you gave it, baz, and it tacks on x squared, okay? And then and it just returns that. It's it's the one and only line, so this is what it's going to return. I could write return this, but it's not necessary because this is the one and only thing that it's doing. Okay, so I could just say do this and return this. Okay, so what this does is the only difference is that if I run the function add square good to foo, okay, it returns 225. So foo is 2, and then I add the square, and it returns 225. And if I ask what is foo, well, foo remains 2. Okay, so if we want to update foo, what we have to do is we have to capture what it returns. So all we have to do is we just say, instead of just running it like this, we just say, well, foo is 2, and then update foo by doing add square good. Okay? And this way, the assignment of the output of the function to the object is explicit. Okay? So we know that when we run this function, we are explicitly taking whatever it returns and assigning it to foo. Okay? Whereas up here, it's not clear that this thing is going to change an object in the global environment. Okay? And that's why probably when we ran this, we might have been surprised that after running this, the thing that changed wasn't bar, but it was foo. Okay? So here it's not clear what is going to be modified in the global environment. Whereas when you have, if all of your functions, if the only way it interacts with the global environment is through the arguments coming in and the returned value going out, then you have to be very clear about what's coming in and where it's going when it goes out. If you just run this without the assignment, it just goes out, and then that value is effectively lost. Okay? So if you want to capture that, you have to make it clear that it is happening right here in this assignment operation. Okay? And so when we do it like this, so foo is 2, we update it like that. Foo becomes 2 and 25. If I want to do this with bar, I have bar is 10. I modify bar, and I make that change explicitly clear right here, and bar becomes 1025, and foo is still the value that we last left it at 2 and 25. Okay. Does this make sense? So how are we supposed to modify things in the global environment? Just write a function as you normally would, and all you have to do is you just make the modification in the global environment an explicit thing. You take the output of the function and you assign it to something. You don't want to have the modifications happen invisibly in the background. When we do something like this, it's not clear what in the global environment is being modified. Okay? And it's only when you look into the function itself, then you say, oh, it's changing foo in the global environment. It's not clear. Like if we're only dealing with foo, sure, maybe we can get away with it. But as soon as just one thing changes, we're probably not getting the thing that we want. Okay, are there any questions on this topic of avoiding superassignment? Because I know this is a temptation to use the superassignment function or superassignment operator in your functions, especially for something like tic-tac-toe where you're constantly updating something like the state, okay? Especially that function that says, you know, update the state by taking all of this. Don't use superassignment there, okay? Just use update state. It's going to return an updated state, and then make sure you just capture that returned value and store that return value into state and overwrite it that way. Okay, well then I'm going to close that, and then we'll take a look at today's lecture. This up here. Okay, so we're going to take a look at object-oriented programming, okay? And so R handles, it's got an object-oriented system. And object-oriented is basically the system that allows us to have functions of the same name behave in different ways based on what we are applying the function to. Okay, so okay, so in real life, this exists. Okay, because if I give you a baseball bat and I say swing, you would take the baseball bat and you would swing like this, right? You would swing like a regular person swinging a baseball bat. Okay. If I gave you a golf club and I said swing, you would not do the same thing. You would change your motion, right? I mean, there's still something similar, but the motion that you do would be different, right? And if I gave you a book and I said swing, then you'd be slightly confused, but you would improvise and do your best at swinging the book around, right? And so that is kind of the way our brains work in terms of object-oriented things. Is given some object and given a command or a function, the way you execute that function is going to be a little bit different depending on the object that you have, okay? The computer has something similar, okay? You ask it to print something, okay? When you ask it to print a vector, it prints a vector kind of just listing all the things out. You give it a list and you ask it to print, it's going to print it looking like a list. Okay, actually those are base types, so technically not object-oriented, but you know, in R, if you guys have created a linear model, and when you ask it to print the linear model, it looks a certain way. If you, there's a function called summary in R, okay? And if you give it a vector of numeric values and you say summary, R is going to like calculate the mean and the standard deviation, and I don't know. It calculates, maybe it doesn't calculate standard deviation. It calculates the min, max, and stuff, right? It calculates some stuff, and that's in summary. But if you create a linear model and you say like y is a function of x, blah blah blah, and you ask summary of this linear model, it prints out kind of like the coefficients and other stuff, right? So that function summary behaves in different ways depending on the object that you give it, okay? And that's what this is all about, right? How do we have the same function behave in different ways, okay? Or something like that. If you are coming from other programming languages, the object-oriented system in R is going to feel very wonky, right? Because most other object-oriented systems, like the ones that exist in C and Python, they behave a different way. You define the methods. Methods belong to the objects, In R, the methods belong to the functions. Okay. If you've never heard of object-oriented programming before, then it's probably the easiest to learn. Well, you won't have the hurdle of trying to not unlearn, but you don't have the other paradigm already set up in your brain. Okay. But so if you never, whatever. We'll go with it, all right? And then, if it makes sense, then great. And if it doesn't, then I'll do my best in trying to explain this to get it to work, okay? So R has 3 object-oriented systems, of course, because we couldn't make it simple, and plus the base types. And the most important thing in object-oriented systems is the class and the method, okay? Class defines kind of the behavior of objects by describing their attributes and their relationships to other classes. So things, we might say baseball bat and golf club belong to the stick class because they're kind of like stick-shaped objects, whereas, I don't know, books and bricks and things would belong to the block class or something. I mean, this is the bad thing. Okay. Well, anyway, so a class defines what an object is, and you might have like specific versions of the class. Okay. Methods are functions. These are basically the verbs, and they behave differently depending on the class of their input. Right. So you might have the stick class, and then a subclass of the stick class would be the bat class. And then another subset would be kind of like the, the golf club class or something. And so the function, the method of swing behaves differently based on whether you have a class of baseball bat, whether it's a wooden or aluminum baseball bat. You're going to swing that baseball bat the same way, okay? And that function or verb method swing will behave differently if you were given a class, an object of golf club class, okay? And classes are usually organized in some kind of hierarchy, and so that if a method doesn't exist for a child, then the parent's method is used, and we say the child inherits behavior from the parent. So you could have class baseball bat, and then further of that you have the specific wooden baseball bat versus the aluminum baseball bat, okay? And we might not have specific versions of how you should swing based on whether it's a wood baseball bat or an aluminum baseball bat, but because you are familiar with baseball bat as a concept, you would swing it like that, okay? Okay, we will talk today about the S3 object-oriented system, and this is kind of the I don't know. Okay. I would say this is the one we're going to spend the most time learning. This is the one that's implemented the most in R. But we will talk about some of the other ones. There's S4, and then there's reference class. But kind of the big thing about R's S3 object-oriented system is that it's called generic function object-oriented. It's generic function object-oriented, okay? And so this is different from the other things like Java or C++, which is message passing object-oriented. And in message passing, we say the methods or the messages are sent to objects, and the objects determine which function to call. So the methods belong to the objects. In R, the S3 system, the computations are still carried out via methods, but you have a generic function which decides which method to call, okay? S3 is very casual. There is no formal definition of classes, okay? So again, if you're coming from another language and you had to define what a class is, that doesn't exist in S3. You just kind of say, I feel like making up a new class today, and R will say, all right, let's do it. Okay, the other systems which I'll mention and we will discuss later is S4. S4 is like S3 in that it is generic function object oriented, except it is more formal and it requires the formal defining of classes and whatnot, okay? And then lastly, we have reference class, and reference class is message passing object oriented. So for those of you who are used to having the methods belong to the objects, reference class is a way to implement that system within R. Okay, and then key thing is that reference class objects are mutable, and we will discuss this when we talk specifically about reference classes, which will be next week on Monday. Okay, and then we have base types, which are not quite object-oriented, but these are the kind of the underlying data structures that exist in R. So these are your vectors and your lists and your matrices and things like that. And they form the kind of the building blocks for the object-oriented system. We can install this package prior to learn a little bit about the object-oriented systems or properties, but I'd say, you know, I think the only time I use this package prior is for this lecture. So, you know, if you're curious about the objects and all of that, then it's a good thing. But we probably don't use it too often. Okay. All right, I'm going to just read this wall of text here. It says, underlying every R object is a C structure that describes how the object is stored in memory. I think we've covered this already. The structure includes the contents of the object, the information needed for memory management, and most importantly for this section, a type. This is the base type of an R object. Base types are not really an object system because only the R core team is allowed to create new base types. And as a result, new base types are added very, very rarely. Okay, so those base types which we covered, the logical, the integer, the double, the character, the complex, the raw, and then you have the list and the function or the closure. Those are kind of your base types, and there's a few other ones like the promise and things like that. But those are the base types that exist in R. We are not allowed to create new base types, okay? So we've covered all of this stuff. Anyway, and you can determine a base type using the function type of, okay? And unfortunately, base type, the names of the base types are not used consistently throughout R, okay? And so, so you have something like, what is the type of a function? And it will say it's a closure, but then you don't say, is it a closure? You say, is it a function, okay? And things like that. And if you say, like, what is this type of, for sum is not a function, it's actually called a built-in, but it means it's a primitive function, okay? So generally most of the functions, like if you were to write a function, it will be called a closure or function. The function sum is a special type of function known as a primitive function, which means it was implemented in C, and it adds up the numbers very quickly by using kind of this the C code, and we don't actually get to ever see the code that underlies that thing. Okay. And then, you know, we have mode and storage mode, which are basically the same thing as type of, but they're holdovers from S. Have you guys heard of S? So anyway, okay. So C was invented at Bell Labs. So a long time. So today, like, everybody wants to work for Google or Microsoft or, I don't know, Apple or something, right? These are kind of like your big tech companies. You know, you go back 40 years, there was only one big tech company. It was Bell, okay? And they managed all the phone lines in the United States. They were like the communications conglomerate. And so if you wanted to do cutting edge work on tech, you would work for Bell Labs. And inside Bell Labs, they developed C for computer code, and then they developed S for kind of statistical work. And then C is still around, and S became open source and became R And anyway, that's how we have it. So anyway, so sometimes you'll see like old ancient S code, which looks a lot like our code and is probably 80% compatible. What does all of this say? Blah, blah, blah. Okay. Yeah, functions that behave differently for different base types are almost always written in C. All right. So even if you never write C code, it's important to understand the base types because everything else is built on top of them. So the base types are all built on top of C. All right. So let's talk S3. S3 is the object-oriented system that is kind of like the default object-oriented system that we'll use in R. It's the only system used in all the base package functions, and it's certainly the most commonly used system in kind of all the packages out there. It is informal, but there is, Hadley Wickham says, an elegance in its minimalism, in that you can't take any part of it and still have an object-oriented system. Okay, all right. There's not an easy way to see if it's an S3 object. You can just say, is it an object? And it will return true, but then that is object will return true for S3 and S4 objects. So the only way to tell if it's S3 is you'd have to say is object, and then you'd also have to check is it S4, and this needs to say false. Okay, or you could use O type in the package prior. So for example, the data frame is an object. It has the class data frame, and it is built on top of the base type of list, right? So we've learned that. We said a data frame is built on top of lists, and indeed, if we ask what is the object-oriented O type of a data frame, it's going to say it is an S3, okay? Whereas if we extract out one of the columns from the data frame, that's just a numeric vector, and the numeric vector is a base type. A data frame is default behavior, takes character inputs and turn them into factors, and factors are S3 object types. Okay, so if we say class, and it will say it's a factor. So again, we said methods belong to the functions, and the functions are known as generic functions. The methods don't belong to the objects or the classes. And how can we tell if something is a generic function? Is that when you look at the code for a function, you will see this thing that says use method. Okay, use method is kind of the indicator that this is a generic function. And so if we go into R, let me just kind of go to the console here. So generally, to execute the mean, you'd have to write parentheses, right? But if you take off the parentheses for any function and you hit enter, it will give you kind of what is the underlying code there. And so here we see use method mean, and this is kind of the indicator that this is a generic function, meaning that this thing will behave differently based on whether I give it, what type of object I give it. Okay. Same thing with print. Okay. Print. If I ask print, we will see use method print. Okay. And this is why the function print, we can just use the same function print for. I can create a factor. Okay, and the way the factor prints, right? So if I say printf, it prints like that, and if I give it a numeric vector, it looks like that. Okay, and the way it prints out looks different, even though if we ask type of f, it's integer, and let me just do I is going to be, and I say type of I, these are both integers, but if I say printf it looks different than if I say print I, right? This is kind of the object-oriented system at work here, that the function print behaves differently based on whether we have. Even though the base types are both integers, if we ask the class of I, it will say it's integer, and if I ask the class of F, oops, it will say it's a factor, okay? Meaning that it is an S3 object, right? If I say is.object of I, this will return false. Is.object F is true, okay? F being the factor is an object, and therefore the function print behaves differently. And if we ask what is print, it just says use method. So this is the generic function, and there are different ways. There's print.default, which is what is used for how it prints out your default things like integers. And there's a separate function called print.factor, which is how the function, this is the code that gets run when we ask R to print an object that's a factor. And you know, all of this, it says blah, 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 all of this stuff, but we can kind of see little pieces such as the part where the levels get printed out and stuff like that. Okay, so when we asked it to print out F versus I, it appears differently. Okay, so again, a function is a generic function if we look at it and it says use method, okay? And if we use the function f-type from package prior, it will say it's a S3 function and it's a generic function. Okay. Some generics don't use method because they're implemented in C, and these are known as internal generics. I would say don't worry too much about it. But the way generic functions are implemented is that they will be written as the name of the generic function dot the class. Okay. So for example, if we have, what is the mean, and it's for objects of class date, it's going to be the mean.date function, okay? And if you want the factor method for the print function, it's the print.factor function, okay? And so this is why most style guides for R today will say don't use a dot as a stand-in for the space, but use underscore, okay? So, because there are some functions like t.test, okay, which conducts a t-test. A better name would be t_test, because t.test looks like it is the transpose function applied to class test, okay? It kind of looks like it would be that, but we know that this actually carries out a traditional t-test. And print.data.frame, we know this is the print function for the data.frame object class. But someone could be confused and they would think, oh, could it actually be the print.data function applied to class frames? And that would be a legitimate question. Now we know that because data frames are such a common thing, we know this is the print function applied to class data frame. But anyway, that's why most style guides would discourage the use of dots in function names. Okay, so we do know, so t.dataframe is the method for t, whereas t.test is the generic function for t-tests. Okay. You can look up all of the methods, okay, all of the special methods that are associated with a function by asking methods, and you give it the name of the function. Or, so you could say methods for print, and it will list off, there's 202 different kinds of objects where print has a specific version of like the way it prints the object behaves differently. So there's, a print.asi as is, a print.bibtext, a print.by, a print. all of this stuff, print.date, print.data frame, print.formula, how all of these things, there's 202 of these different things here, right? And RStudio has a nice little thing where if you just type in print dot, and then it starts listing them all off, okay, or a whole bunch of these. Some of these have stars and stuff, but and I don't actually know what those stars mean. But so you can look up what are all the different methods associated with a generic function. Okay, or you could say what are the different methods associated with a certain class. So if we want to say methods, what are the methods that exist for class equals factor? We can see there is subsetting and double bracket subsetting, subsetting with assignment, and there's also all.equal, as.character, as.data frame, and all sorts of other functions that exist, or methods that are specific for factor. So there's going to be a print.factor, a plot.factor, and things like that. Okay, what if we want to create our own class? We can do this. All we have to do is we just say, we can use the function structure, okay? And we can say, take whatever object it is. Here I'm creating an empty list, and here I just say class is foo. And boom, I've created a new object of class foo. Or, even easier is you just create your empty list, and then after the fact, say, you know what? I'm going to change the class of this thing from list, or from whatever it is, it's a base type list, but we're going to say it's going to be class foo. Okay? So that is, that's it. That's all it takes to define a new class. You want to call this happy awesome class? You can do that, okay? You just do class of whatever object it is, and then you put in quote a character string that names the class. Okay, and then in our just remembers this. So if I say so right now I've got bar, okay, and if I ask what is the class of bar, it's going to say it's a numeric thing. But I can just say, okay, you know what? Let's change class of this object bar to fun times class, okay? And then that's it, okay? Bar is now of class fun times. I can ask, what is the class of bar? And it is a fun times class object, okay? We can say, does it inherit from another class, okay? And so we can say, does it inherit from some other thing, and it will return true if it does. Or if there's a hierarchy, then it will also do that. The class itself can be a vector, okay? So for example, if you create an object of class GLM, which is generalized linear model, it inherits from GLM and then LM. And this tells R, if you find methods specific for GLM, use that. But if you don't find a method specific for GLM, but you do find a method for LM, then use that. And if you don't find a method for GLM or LM, then just use the default method, okay? So, so there's probably a print.glm object, but there might not be some other method that exists for, I don't know, maybe there's a plot for LM but not GLM, I don't know, I'm not sure. It will tell R, if you find something for this, use this, and if not, then try to search for this and use that, and if not, just go with the defaults. Okay, so you can give it a vector of the classes, vector for the classes there. A lot of times the classes will have a constructor function so that it will create an object of that class, much like factor, okay? So there's a function called factor such that whatever you put inside the factor function gets created to be an object of class factor. Okay, so here we are creating a function called foo so that whatever we put in foo will get returned as an object of class foo. But so oftentimes that's a nice thing to have, but it's not necessary. Again, all you have to do is just say class of this thing is some character string. Okay. But apart from the constructor functions, S3 has no checks for correctness. So here, we're going to create a model, and we're going to say, make a linear model between the log of miles per gallon and the log of displacement from the data, MT cars data set. Okay? And we ask, what's the class of the model? It's going to say it's a linear model, LM, class LM for linear model, right? And we say, print this out, and this is how objects of class LM get printed in R. It tells you the call and the coefficients. But let's say, for whatever reason, I say, you know what? Let's change the class of this model object to a class of data frame. Okay? R says, all right, that sounds silly, but I'll do it. Okay? Actually, it doesn't even complain. And then, so we've changed the model class to data frame. And then now I say, print this out. Okay? And it prints it out. It did its best, and it says, I've got 0 rows. This feels weird, okay? It's not that we deleted any of the information. All we did was we just changed the class. So if I did like model $ coefficients, those values still exist. They're just when you try to print it out as a data frame, R doesn't know what to do because the LM object is built on a list with vectors of different lengths. And so, there's no check. When you just change the class right here, there's no check. It doesn't try to feed it into data frame and say hey, you know what, you're giving me a list with objects of different lengths. It's not going to work. It just says, okay, I tried. Sorry. And this is what we have, okay? So, Hadley interjects here and says, if you used other object-oriented languages, this might make you feel queasy. And it says, but surprisingly, this flexibility causes few problems. While you can change the type of an object, you shouldn't. And it just says, R doesn't protect you from yourself. You can easily shoot yourself in the foot. But as long as you don't aim the gun at your foot and pull the trigger, you won't have a problem. So just don't do stupid things, and you'll be fine, right? Okay, what if we want to create our own generic functions? We can do that too, okay? And maybe we'll need to talk about this some more. Here I'm going to create a function called f, and this is going to be a generic function that says use method, okay? This is all it takes. All it takes to make a new generic function is to say the function of this is going to be use method f. Okay, so what does this do? This then requires us to create specific functions for different class types. Okay, so here, if I just do this and I say run f, R is going to complain. It's going to say I don't know how to do this thing. Okay, but then so I have to create something called f.className. So my first thing will be f.a, and this will be the function that gets run when I provide it an object of class A. Okay, and so this function is it's a really silly function. All it's going to do is return the character string class A. Right? And so now I'm going to create an object called A with it's a blank list where the class is equal to A. Okay, so what is the class of A? It's A. And then if I run f on A, f gets executed, and it says use method f, and use method f says, oh, let me check what object type this is, and it says, oh, it's class A. Let me see if I have a function that exists for class A of function f. Ah, I do. It's f.a. Let's run the code for that. What is that going to return? It just returns the character string class A. Does that step make sense? So when we say f and we give it this object A, R says, wait a second, this is a generic function. I've got to find the appropriate method. Use the method here. And it says, okay, well, let me look up the class. The class is A. Do I have a function for f.a? And the answer is yes. Okay. I can then, I can add specific methods for functions that already exist, such as the mean function, right? So here I'm going to do mean.a. This is a special method for special version of the mean function where it's just going to return the character string a. Okay, this is like a terrible mean function, but now when I say take the mean of a, right? A is just an empty list that just happens to have the attribute class equal to a. So normally if I say take the mean of an empty list, R is going to say I can't do this, or it's going to, I don't know, what is the mean of an empty list? So if I say mean of list this, okay, it's going to return back NA, right? But now that I said, hey, you know what, there's mean.a, okay, when we run mean, the mean has use method, so R says, okay, let me see, do I have a method that exists for objects of class A? It says, oh yeah, I do actually. It was just defined right now. And it says, okay, I'll run that, and therefore I'm going to return the character A. All right, looks like we've run out of time, so I have more to say about S3 stuff, so we'll continue talking about this on Monday, but we'll talk more object-oriented stuff. Okay, and avoid using super assignment, okay?